So we've looked at velocity and we've defined it as this change in x over change in time. If you like, it's rise over run, it's a slope. And so if we look at this example, which we looked at last time, that shows you position versus time, we can find this velocity at points along here if we can just find the slope. So if I look at this, I've got the slope here. We looked at that one. And if we look at this, we've got the slope here. And notice that the slope is changing, right? This is a steeper slope. And this is a flatter slope. This is almost zero. And in fact, a flat slope tells you a v equals 0, right? Because that would be a slope of 0. So this is a situation where you've got somebody going from the point 5 meters up to 10 meters, and they're starting out basically at rest if I have a flat, completely flat slope, and they're speeding up. So you can think of somebody getting off the starting blocks, for example, and so they're speeding up. And so if we have a changing velocity, then we call that an acceleration. So I don't think you'll be surprised to see that an acceleration we define the same way. This tells us about how much the velocity is changing. Velocity is changing. And it's defined in the same way. We have an average velocity, which is delta v over delta t, our change in velocity over time, which in this case is just going to be v final minus v initial over time final minus time initial. Usually we set our time initial equal to 0 in whatever direction. In this case, in the x direction. We're staying in one dimension. We're staying at in the I hat plus or minus I hat direction. So that would be our average acceleration. And so I don't think you'll be surprised to learn that this is a derivative of your velocity. Or if you like, your acceleration is just dv dt in the I hat direction, and this just think of again as a slope of your velocity versus time curve. And so if we were going to do that for this setup, I would say here's velocity, here's time, velocity versus time. Well, right here at this point, that would be a velocity of 0. So I would put that in, right, because it would be flat. And then somewhere later on, at 2 seconds, I've got a positive slope and it's getting bigger and bigger, and it might be that we just go and it's fairly linear. Okay, it might be that velocity versus time, we're speeding up constantly. We're going from 0 miles an hour up here to, well, our average was about 5 halves. So right about here, we would be at about 5 halves meters or 2.5 meters per second, and maybe all the way up to 5 meters per second at the end. Okay, so that's a possible description of this motion. And so all I've done is said, hey, my slope gets bigger and bigger, and maybe it gets bigger and bigger in a linear fashion. In which case, if it's linear like this, if velocity versus time is linear, notice that your average velocity is equal to your average acceleration is equal to your acceleration at any time if we have this linear v velocity versus time plot. And we're going to see this a lot. There are a lot of instances where this is the case. And so mathematically, it's easier to work with this case, and this gives us a lot to work with. So we're going to see this a lot. In other words, we have a constant slope, right? The slope at this point is, oh, that's not a very good slope, is the same as the slope at this point, is the same everywhere. So constant slope, we have the same slope. So that means we can, when we do this delta x over delta t, we can pick any points we want to find that. And so our average velocity is actually, our average acceleration is equal to our instantaneous acceleration. So this is the case that I've drawn for a constant acceleration. Now, that doesn't always have to be the case. I want to point out it's possible to have, say, a velocity versus time graph that looks let's say something like this. Okay, that's for oscillations. And if that's your velocity versus time graph, then you have to be fairly adept at taking a derivative. We're not there yet, to find then our acceleration versus time. But this is not going to be constant, right? So our acceleration is going to vary. In fact, my acceleration is 0 here and here and here. It's positive at that point, so it might look something like this. For those of you who have done these kinds of derivatives. I'm just taking the derivative graphically, and this is a negative slope right here and here with my maximum right at this point, so I'll go to about here, and it turns out, for those of you who know, right, if this is a sine wave, then the derivative of the sine wave gives you a cosine wave, so this is my cosine wave down here, okay? But in general, we're going to be doing, at least to start with, we're going to look at constant acceleration situations, okay? And so we're going to look at situations where our velocity versus time is a nice linear graph, and that turns out to be the case, that our position versus time turns out to be a quadratic. Okay, I also want to say something before I go in too much more into actually calculating these. I do want to say something about directions here. Okay, so something about directions. This is our x-axis, right? And we can be moving. So we can think of this as just a north-south axis if we want. If we're going from Eckerd north, that might be the positive direction. South might be negative. East-west, it doesn't matter. But this is one direction. This is just in the x direction along a road. And if we're going, say, to the right on this graph, say we're going 30 miles an hour, and we're speeding up, so this is the direction of the velocity, and we're speeding up, then the acceleration is going to be in the same direction. So in both of these cases, they're both going to be positive. Okay, if instead we're going 30 miles an hour, with the velocity still in that direction, and we've got this, if we've got an acceleration that's opposing the motion, what it's saying is that the change in velocity is in that direction. That means we're slowing down, right? This is slowing down. Because the acceleration is in the negative direction. It's opposite to our velocity. But a negative acceleration doesn't always mean slowing down, because these signs are a little weird, okay? So if instead we're going this direction, this is our velocity, is in this direction, so we're going 30 miles an hour in the minus I hat direction, then if we have an acceleration that points in the same direction, that's speeding us up. So we're going faster. So even though our acceleration is in the negative I hat direction, it's still going faster. We're speeding up. And similarly, we could have a velocity that's going this direction with an acceleration in the opposite direction, and this would be slowing down. So the signs here, the takeaway is that the sign or the direction associated with the velocity tells you the direction you're going. So north would be a velocity direction. Acceleration tells you whether you're speeding up or slowing down. If it's in the same direction, then you're speeding up. And if it's opposite, then you're slowing down. So if we look, for example, our acceleration down here is in the positive direction, right? That's the positive direction. But because it's opposed to the direction you're going, so you're going 30 miles an hour south, but your acceleration is in the other direction, that means you're braking, you're slowing down. Okay, so that's what the signs mean. And I think it's useful to kind of hold on to that. You may want to put that on your equation sheet somewhere just to help you out so that you can check to make sure things make sense. So you know what a positive sign or a negative sign is telling you, right? Because it doesn't mean negative, doesn't mean bad things are happening. It just tells you something about the direction.